Hello, I'm Ibrahim Imam, and welcome to this episode of the Neurology Lounge podcast. In this episode, we will continue our exploration of the history of the brain and of neurology. The last episode on this subject was titled Inception. There we looked at the early history of the exploration of the brain. In this episode, I'll be speaking to Matthew Cobb, author of The Idea of the Brain. We'll be discussing his perspective of the evolving concepts of the brain over time. Matthew Cobb is professor of zoology at the University of Manchester, where he studies the neurobiology of the sense of smell. He's also a non-professional historian, having written a number of books, most recently Life's Greatest Secret, The Race to Crack the Genetic Code, and The Genetic Age, Our Perilous Quest to Edit Life. He is currently completing a biography of Francis Crick. I can't wait to read that. Matthew Cobb, welcome to the Neurology Lounge podcast, and I'm most grateful that you accepted my invitation.
Well, thank you for inviting me. It's good to be here.
Thank you. The usual first question I ask my guest is why they wrote the book. You want to?
Yeah. Well, I think it was suggested by my editor. This is a trade book, what you call a trade book. So it's not an academic book published by a university press or anything. And so trade publishers, which are the ones that you see in most bookshops, they will have they'll suggest things to you. They will sometimes say, "Oh, I've got this great idea. Would you like to write it?" So my then editor suggested, I think, that I write a book about the brain. This was in about 2014 when I just finished the book Life's Greatest Secret, which was all about the genetic code. And I was a bit kind of taken aback. I mean, I have a degree in psychology. I am probably something like an evolutionary neuroscientist, in that I'm interested in the evolution of nervous systems and how they function, in particular sensory systems, and in particular the sense of smell. So it wasn't completely alien to me. And I thought, okay, well, that could be a bit of a challenge. Why not? And I started writing, and frankly, it was awful.
Oh, dear.
What I was writing was so boring. I mean, I found it boring. And it really wasn't very good at all. And it was only quite late on in the process, when the whole book took me 4 or 5 years to write, that I realized that I could make it interesting. And what was interesting was something I'm sure we're going to talk about quite a bit, which is thinking about the metaphors that are used to understand and describe the brain. And that once I had that kind of conceptual breakthrough, then I could go back and rewrite all the early chapters, which were just kind of one damn thing after another. And as I say, very tedious. Chuck out loads of unnecessary detail, and then kind of put it into this novel. Well, it's not novel, but it's novel for books about the brain, novel framework. One last little story is that my subsequent editor, because my first editor unfortunately died, at one point in the he was reading a draft quite late on, and he said, there's something missing from this. I said, "Oh, really?" He said, "Yeah. How does the brain work? You don't say." I said, "We've no idea." He said, no, you can't say that. You've got to have an explanation. Every book about the brain says it's some kind of mega computer, or it's something to do with quantum woo, or who knows what. I said, yeah, but none of that's true. The actual truth is we do not know. And that's what the book's going to be about. So you better accept it, because I'm not making up something that neither I nor anybody else will believe. And as it turned out, I think that's actually been part of its success, in that neuroscientists and neurologists and psychiatrists have all been remarkably generous, because I tell the truth. We don't know what's going on in there. We got a rough idea, but actually how it works remains a mystery.
Yeah, you have a lot of pseudoscientists out there who know exactly how the brain works.
A lot of them are physicists for some reason. They seem to think that this is going to be easy. Quite the opposite. Physics is pretty straightforward, but brain behavior, now that's the big problem.
And I suppose as a zoologist, you couldn't have written this book about animal brains. It had to be human brain.
Well, it's not just about, I mean, I would disagree about it. I mean, it's not about, although much of it is about the human brain, in particular, the later part. I mean, the book's divided into what I rather facetiously call three halves. So it's the past, which, again, this structure actually emerged right at the very end, which of writing the book, I realized I needed to guide the reader and really make it obvious what I'm talking about. So there's the first of the three halves is about the past, which basically goes up to the 1940s, 1950s, with all the various metaphors that we use to understand the brain. And then the second of the three halves is about the present, which is describing the current metaphor we use, which is the computational and the computer metaphor, and looking at everything that's happened basically in the last 70 years and making what can seem to be quite a bold statement that we haven't really progressed much in the last 70 years. We're in this particular worldview, and although there have been huge discoveries, there's nothing really has changed in that period. And then the final part, which was again insisted by my editor, he said, well, you've got to write about, okay, you don't know how the brain works, but how will we understand it? Okay. And, you know, scientists don't really like making predictions, if they've got any sense. So I didn't really want to write that, but I had to. So there's a third half, which is very short, about the future, trying to see where we will go. And as I say, that structure emerged very, very late on with the tussling with a commercial editor. And that's quite interesting because, you know, if it had been sent to an academic press, they would have been quite happy with probably the really boring version that I'd written at the beginning. But trying to struggle with somebody who's got very clear ideas about what the informed lay reader, who it's primarily aimed at, what they would want, that actually produced something which I think was much more interesting than my rather more academic instincts would have produced.
Well, it did make for very interesting reading, obviously. Of course, a lot of history. You said the first part is about the past, and it takes me back to what you said. For most of our past, we have viewed the heart and not the brain as the fundamental organ of thought and feeling.
Yeah.
Why was the heart thought, I can guess, but why was the heart considered the center of intellect?
Well, it wasn't only the heart, it's also the liver and the kidneys. All sorts of organs have been localized, which looks very funny to us now, looks very strange. I think the simplest answer to the heart-brain business is that it doesn't, what it actually feel. What does it feel like? What does it feel like to be human? Where do you feel excited, fearful, emotional? You don't feel it up in your head. No, that's just crazy. You feel it in your body. And Carl Jung, the great psychiatrist or psychotherapist or psychoanalyst, he talked with one of the leaders of a Pueblo tribe in southern United States, and this is in the 1930s. And this person said to Jung, we think the white people are mad. We think they're insane. And Jung, took this in his stride and said, well, why? And he said, well, you believe that you think with your brain. And Jung now really was taken aback. So he said, well, where do you think that you think? And he puts his hand on his heart and he said, we think here. And that's what it feels like, right? So, you may know from your, you've been told that it's all about your brain, but you can't just work that out by introspection, by thinking about it. Because if you just think about it, okay, you might have a sense that your sense organs are in your eyes and your ears, but that's all. Your heart pounds when you're excited. If you're frightened, it's your guts that churn. Everything is to do with your body. I mean, there was a famous article in Trends in Neuroscience, it's about 20 years ago, that had the rather daring title, "The Brain Has a Body." Which is actually, clearly absolutely true. You are not a brain in a vat would not be a human being. We are embodied in all of the experience that we have, from the hormones, from our blood sugar levels, from all that stuff. clearly affects our brain activity, our mood, our behavior, our feelings. So I think that the real answer is that it's very, very hard. And we only know that it's in the brain because we've been told it. We couldn't figure that out ourselves. It's really, really difficult. Because one final word, the lesson that I always emphasize to my students whenever I give a talk about any aspect of scientific thinking in the past, which often looks quite amusing because we know it's right, how wrong it is you're not allowed to think that people in the past were stupid, because those people were incredibly smart. They're just as smart as you and me, in most cases, much more so. So the problem then comes is, well, why did they believe what they did? If we think that's incorrect, and we've got evidence to suggest that it is, why did they believe that? And one really good example of that is, well, people used to think that the sun went round the earth. Well, what does it look like? It took an awful long time. If you just wanted to work out, you would imagine that was the case. And it took a great deal of effort to work out that, in fact, it must be something else and that the earth is going around the sun, not the opposite. So, everyday experience leads us to certain conclusions, which eventually scientific discovery can prove are incorrect. But that experience is incredibly powerful.
Yeah, but it's interesting that a whole group of people on age will think one way, and then one person thinks differently. And in this case, the person you mentioned with the cardio-centric view who criticized it was Alcmeon,
in
the 5th century BC, who thought, no, it's not the heart, it's the brain. I think probably the first person. I've never heard of him. I don't know why we know so little about him. Who was he?
Well, we don't know. So he was a philosopher, he's a Greek philosopher. I mean, I think you've got to remember about all this, and I did my best to not simply stick to the Western canon, the ancient Greeks and all the rest of it. But we've got a real problem because they were very clever and they developed a way of thinking that is still extremely influential. And above all, they left written records. So people may have had all sorts of astonishing ideas around the planet, but if they didn't leave a written record, it's very hard for us to understand anything about them or even know about them. And even when there are written records, in the case of Alcmeon, is that none of his original writings survive. And so what there are commentaries on lost manuscripts, which may have been written 300 years later. So we don't actually know much about him, where he was from, we know vaguely where he was from. He's from the southern part of Italy, because the Greeks occupied all that area. But we don't know anything about him in particular. We just know that he emphasized the role of the brain. Why he argued that is very hard to tell. He may well, as I say, you can, without doing a human dissection, and by kind of assuming that humans are animals and, well, they're very similar to animals. Clearly, if you're preparing a goat's head soup, then you'll get the head of the skull of the goat, and you'll be able to see its eyeballs and see the optic nerve going into the brain. So there's lots of reasons to think that some relatively primitive dissection, which might have been culinary in purpose, could tell you, well, all these sense organs are going to the brain and they're connected by these fibers. The Greek word for fiber is neuron. So there's some kind of connection, but that doesn't necessarily tell you which way it's going. And we know that Western thinkers, for example, about vision, thought that even in the 17th century, thought that rays came out of the eyes. So what looks to us now like a transmission route from the eye to the brain, you could have argued was going the other way. It was a kind of way of sending out sight rays that then bounce back and enable you to see things. So, I'm very wary. You'll do forgive me. I know that medics in particular are very keen on firsts, and the medical journals are full of brief little articles about, great heroes. Historians of science and medicine tend to be much more nuanced and to be wary about pinning great discoveries and insights on particular individuals, because often when you actually look at it carefully, we now interpret them as having this great insight, and Alcmeon was clearly correct in focusing on the brain rather than the heart. But he didn't have anything like our understanding of what was going on, and because the documents have been lost, it's very difficult to do more than kind of give him a gold star without really knowing what he was actually arguing.
Well, I suppose we know more about Galen, who followed in his footsteps, who essentially put the cardio-centric view to bed, and he did that with these grisly demonstrations you talked about. We again malign Galen for getting so many things wrong, but I think the view is changing. That in his time he was very good, wasn't he?
Yeah, he was extraordinary. I mean, he's generally remembered as the father of what passed for medicine in the West for about 1,500 years, which, even if it's a load of nonsense, although we could discuss the links between the four humors, which he kind of codified, and ideas about people, having low levels of serotonin or whatever. There's if you replace serotonin in much psychiatric speak with yellow bile or whatever, it sounds quite similar. But Galen, I mean, that was my impression about Galen. Yeah, he had made this contribution to medicine and so on. And then in reading about him, I was absolutely blown away by quite how significant a figure he was at the time, because he was a poet, he was a philosopher, he had an absolutely immense library, he was the physician to the Roman emperor. I mean, he learned his trade looking after gladiators who'd been kind of hacked about in the arena. And one of the things he noticed was that if there was chest damage to the front of the body, in particular, something which he was able to identify, the left recurrent laryngeal nerve, which has this bizarre pathway which goes from the brain and loops down underneath the aorta and comes all the way back to the voice box. Something which, I often use this, is used as an example. You can only understand in terms of the evolutionary past of humans and their developmental biology, and no designer would ever make this nerve that you just have it going straight to the voice box from the brain. But what he noticed was that this damage to this would cause damage to the ability to speak. And he then wanted to argue that the voice was being seen as a particularly significant demonstration of consciousness, clearly in humans, but even in animals. And this extremely unpleasant demonstration that he did, which was actually a kind of public argument. So he got an opponent who argued that the heart was fundamental in producing the voice and consciousness, and he did a really unpleasant demonstration with a pig. And of course, this is done in the first century, the Common Era, so the pig's conscious, or whatever a pig is, but it's awake and it's not happy. So this pig is strapped down and held down by kind of chains on a dissecting table, or a vivisecting table more accurately, and in front of a group of kind of witnesses, Galen challenges his opponent, and they open the pig's chest, and so its heart's beating and it's making horrible noises. And Galen says, right, put your hands round the heart, stop it beating. So he holds the heart and it stops beating. And of course, the pig carries on squealing. It's still unhappy. It's still conscious, at least for a certain amount of time. Eventually, obviously, it will stop. But they then open the skull, which must be even more awful. And Galen then presses down on the brain, and the pig immediately becomes unconscious. And he goes, there you go, it's the brain. Now, what's striking about this is, you said this debunks the heart-centric view. Well, yes and no. I mean, we think it did, but people at the time didn't, because everybody went, no. Aristotle says that it's the heart, and the brain is just some kind of radiator for cooling stuff. So Aristotle's a pretty smart guy. He's said lots of things that are right. So we're going to go with Aristotle. On the other hand, Galen's ideas about bleeding and all the rest of it, that looks pretty cool too. So we'll keep that bit. And I mean, Galen was, he came up with the two semens idea, whereas everybody like Aristotle was saying that it's the male that provides and puts and imprints his form on the female menstrual blood, which is going to form the future fetus, Galen actually suggested, no, there are two equivalent semens, one produced by the male, which is the obvious stuff, and the other produced by the female, which I can't actually see, but it must be there. So, I mean, again, in terms of understanding what we would call reproduction, he was extremely smart. And although people knew about all these ideas, they weren't, and they were preserved and transmitted thanks to the Arab tradition, because obviously, to be very crude about it, Europe collapses. The Greek manuscripts are preserved in the Caliphate in Iraq and Iran by Arab thinkers. And that then leads to the preservation of these ideas. Interestingly, they don't, though they're very, very interested in things like chemistry and maths and algebra and all those owl words that we use obviously come from that tradition. They didn't develop much in the way of medicine or anatomy. So there's kind of a stasis in many respects. And Galen's idea repeated, and this is what wisdom was, knowing what the ancients were. And then you could also develop it with optics and chemistry and so on, which clearly those astonishing Arab thinkers did do. And then eventually all this is retranslated back into Latin. So it's gone from Greek to Arabic to Latin in the kind of 12th, 13th century. And then the West really discovers this stuff and goes, oh, this is really quite amazing. But they're still holding with their Aristotelian ideas. And in a more general sense, they're trying to fuse this with Christianity. So Western thinking is unbelievably confused about everything because it's got these lots and lots of bits it's trying to put together. So it's, Galen was incredibly influential, but the real shift, I was quite fascinated to see, you can actually see it in Shakespeare. So the real shift comes in the late 16th, early 17th century. Well, and Shakespeare in The Merchant of Venice has one of those songs that you skip over when you're at school because it's really boring. There are people dancing on the stage, and it goes, "Tell me where is fancy," so imagination. "Tell me where is fancy bred, or in the heart, or in the head." So what's significant about this is that Shakespeare, one, knows that people aren't sure and they're arguing about it. Two, he knows that the groundlings, who are the people who are standing up in the Globe Theatre and are going to throw rotten cabbages if they don't like the play, that they will know too. So this was something that was, in common culture, that, well, there's the heart, but there's also the brain. What's going on? Well, those clever people don't know. Sure feels like the heart to me. And you can hear that heart business. I say this at the beginning. If you just think of those phrases, he wears his heart on his sleeve. My heart was in my mouth, and all the rest. Why, if you're in love, is the symbol of heart? Nice. And all these kind of linguistic fossils. They're conceptual fossils, but they still got power. And if you imagine replacing the word heart by brain,
it doesn't work.
They just sound weird. And it's not just because we're not used to them. It doesn't fit. So the heart and emotion and feeling is still very much with us, I think. Sorry, I got a bit lost in there. But anyway, we got up to the 17th century.
Yeah. And then I think Thomas Willis kind of came into the field there, and his contribution was moving the seat of thought from the ventricles to the cerebrum. And I just wondered, why did they ever think the ventricles were responsible for thought?
If you're going to say something's in the brain, and you look at a brain, and eventually from around about the 13th century, so before Vesalius, but Vesalius obviously produced the coffee table book of extraordinary dissections in his final volume, I think there's 8 volumes in total. The final volume is on the brain. Then it's a real kind of lumpy mess. There's lots of stuff there, but you've got these holes, and that idea goes back to about the 3rd or 4th century, that various thinkers had suggested, well, if thought is, maybe it's like wind. So this is the idea of the animal spirits. That animal doesn't mean like an animal. It means motional and producing motion. They're animated. If you've got these kind of spirits, maybe it's like the wind, and then you've got these holes in the brain, these big gaps. Maybe that's what's in there. And so there was a theory that out of the major ventricles, that each one was to do with memory or emotion. So this idea of localizing function to a particular part of the brain, even if it's a fluid-filled ventricle, was popular, but I mean, it was quite obscure in that the average person in the street wasn't going to go, oh, my ventricles are playing up, you know. I don't think they knew about that, but they were written in learned manuscripts. And one of the things Willis wanted to do, basically said, look, these are just fluid-filled cavities. The real action's going on with all this unbelievably complicated neurons that you can see, or you can see the neurons, but you know, the nerves and the organization and everybody's favorite structure, the circle of Willis, and all the rest of it. So Willis was very significant in that respect. But I mean, it's, you know, it's hardly surprising in 1670 or 80, whenever it was, that he's not really able to go much beyond that. I mean, it is, you know, so complicated that to come up with an explanation that is useful in terms of science, or even more difficult in terms of medicine, that was, you know, quite understandably beyond him or anybody else at the time.
Yeah, a victim of your own time, I suppose.
Yeah, absolutely. Yeah.
And then it brings us to this view of the brain as a machine, and just advanced by somebody I didn't know about, the Dane Nicholas Steno.
Yeah.
And I think he was the one that dismissed the idea of the animal spirits and became a bit more.
Yeah, Steno's quite an amazing chap. So he did lots of things in a very, very brief amount of time. So he's a physician. He trained in Leiden, which was probably the best medical school in the world at the time in the Dutch Republic. And he, amongst other things, he also discovered that women have eggs, which he just kind of said well, not only women, he said that in viviparous organisms, because he was dissecting a dogfish, which is a kind of shark that has it produces live bearing produces live offspring, not an egg. He said in viviparous organisms, and he was including women in this, the female testicles, as they were called at the time, that is the ovaries. He says the female testicles are like the ovary in an oviparous organism. And he just kind of says this in a throwaway comment. He did that. He basically invented geology. Okay. Because he went into the Tuscan hills, and they discovered these stones that were called vipers' tongues, because they kind of look like arrowheads. And he picked one of these up and he said, "This is a tooth. This is a shark tooth. I know, because I dissected a great white shark on the Tuscan coast the other week. These are teeth. Okay. So how do they get here? So look, we can see layers in the rocks." And he came up with what's called Steno's principle of superposition. So you obviously didn't do a geology GCSE or whatever. And Steno's principle of superposition says that the new stuff's at the top and the old stuff's at the bottom. So he comes up with this idea, and fairly obviously his answer: how did the sharks get to this mountaintop? Well, there was a flood. It's in the Bible. So there you go. He's found the explanation for it. He also discovered how muscles work, and his explanation of that was basically correct. And he made these very famous dissections of the brain in the late 1660s in Paris. And he basically says, look, the brain is like a machine, and if we can take it apart, we can understand how it works. And this was one of the clearest principles of, one, how to proceed scientifically to understand what's going on, and secondly, the really explicit linking of understanding the brain with the current technology. Now, people had done that in the past because that's what the animal spirits were about. They were thinking about wind power and so on. Whereas Steno was now trying to link it to understanding of primarily a mechanical understanding to do with clockwork and so on, and all the latest technology and levers and so on. That worked well for him when he was trying to explain the muscles. But when it came to the brain, it was a bit tricky because there are no cogs in there and there are no kind of tendons pulling on things. And what it does is much more mysterious. But this principle, I think, of how you should go about understanding what's going on, I think was really quite brilliant.
And you said that concept drove the scientific understanding of the brain for many centuries. Is there anything left in it that's valid today?
Well, I think the general approach is right. I mean, it's tricky because one of the main ways that people have understood how the brain works, but also how genes work, is the principle of ablation. That is, you take something out and a system stops working and you go, aha, this is essential to that system. And that can be accurate. And we'll talk about this when we get onto the 19th century. It can give great insight, but it can also be horribly wrong. And ablation can, either through injury, illness, or experimentation, can be remarkably insightful, but it's very tempting to lose sight that you're working on a whole system. And if you take one part out or damage it, you may be actually just producing an imbalanced system and not necessarily something that's insightful into the actual function. But I think his basic idea, it still holds. That's largely what people do.
Knockout mice comes to mind.
Absolutely. So knockout mice is where you damage a gene or you stop it working. And one of the most remarkable things happened was when people got very excited about this, and then they discovered that loads of these knockout mice, which had no gene function for what was supposed to be a really important gene, they were quite happy. The system was buffered, you could say. So although this can be a powerful technique, it can also produce very mysterious and misleading results. So I think, care is needed.
Yeah. And I suppose that's behind the drive to move away from using animal models to describe a lot of neurological disorders.
Well, yeah, I mean, I'm always very torn about this. So I've spent although I have a degree in psychology, I've spent my whole career trying to understand the behavior of insects, and in particular of Drosophila. So I've had a very reductionist approach, and certainly for the last 20 years, I've been studying the activity of single cells in the larva, in the maggot of the fly, this tiny little structure, because it's so simple. But on the hope, confidence, belief that you can extrapolate from those very simple systems to more complex ones like human beings. And clearly animal models have been remarkably influential. I mean, I have colleagues who work on models in the same system, so a Drosophila larva, of epilepsy. And they can study neurons in the body wall of the larva, and then it can produce epileptic-like symptoms, and you can then treat this with various drugs. And so you've got a model system for at least trying to do a first screen of particular medications that may be able to alleviate conditions. So I think that animal models are very important, at least for getting an initial grasp of what may be going on, including in some rather unusual animals like maggots, which probably isn't what most people think that the kind of work's being done on.
Interesting. And then came what you call the anti-machine view, advocated by Gottfried Leibniz. And he compared the brain to a mill, because the interaction of the parts are not sufficient to explain the output. Is that an accurate reflection of?
I think it's kind of that. I mean, and that's one aspect. So what Leibniz said, he said, look, all you people trying to understand what thought is and so on, imagine the brain's a huge, great big mill, the most complicated machine he could imagine. You've got lots and lots of moving parts, big things whirling around, and stuff being ground up if it's a flour mill or whatever. And you go inside this, because you're writing in the early 18th century, you go inside this brain mill thing, could you show me where a thought is? And of course, the answer would be, well, no, because we've no idea what's going on. The problem is, we're still there today. I mean, Leibniz was partly arguing this because he did not accept a materialist explanation of thought. And this is the tension that has continued. I mean, it's slightly abated now, but there are still dualists. So there are people who, and certainly Sir John Eccles, who was one of the most recent advocates, leading neurophysiologist in the 20th century. He was a profound dualist. That is, he believed that human thought was non-material. And this idea was codified by Descartes in the 17th century, who again argued, well, you've got this structure which somehow allows the ideas and thought, which is from and let's call it another dimension, to enter into our world and then to produce thought. Now, he was, many people who wrote to him thought this wasn't terribly impressive, was a bit vague, and what do you actually mean by this? And of course, he couldn't explain, and that continues down to the present day. But of course, they got a killer argument. Okay, right. You're telling me that it's all just neuronal activity, it's all just neurochemistry. Show me a thought. To which, and you go, well, no, I can't, right? How does it work? How does the activity of one set of neurons produce thought, whereas another set of neurons could be in your elbow, or it could be in parts of the brain? How does that not produce the thought? What's going on there? And of course, we've got no answer, right? We've got hand-wavy explanations, but really, this is we're just saying there's no evidence for a non-materialist explanation of thought. All the evidence goes in the other way. I mean, when I was a rather glib undergraduate and I read about Descartes, I thought, did he ever drink a cup of coffee or have a glass of wine? Because, the material world is immediately affecting your thought processes by this stuff that you're putting into your body. So if there is an interaction between some weird stuff that is non-material and our body, it's two-way. It's not just that this stuff comes in and then fills our brain, but clearly our body, as we said at the beginning, can affect the way our brain functions. This is, on the one hand, it's trivial, but it's also extremely significant. How that works, nobody's got any idea. And I think it's really important to emphasize that we really do not understand how these things work.
And I suppose the anti-machine view is supported by the fact that we still haven't identified where consciousness lies in the brain.
Yeah, absolutely. I mean, what can you say about consciousness? Not very much. I mean, there was a very famous paper written by, there was a dictionary of neuroscience written by Stuart Sutherland, who was a British psychologist, and his entry on consciousness, this was in the late 1970s, his entry on consciousness said, consciousness is a very complicated phenomenon. Not much worth reading has been written about it. And you could argue about whether that's still the case, kind of 40 years on. But what is absolutely obvious is we don't know how that works. And the most striking thing, or particularly might alarm any listeners who are about to go under general anesthetic, is that we know that the general anesthetic makes you unconscious. And then they turn off the gas and you come back, right? It's magic. The anesthetists know what they're doing. They have no idea how it works. All we can say about consciousness is that it is soluble in those gases that you breathe in. How that does it? No idea. And clearly for physicians have rather different criteria to scientists, because as far as you're concerned, ultimately, the key thing is, does it work? Is it safe? Does it work? Will it solve my patient's problems? And that's what, if you're ill, that's what you need. I'm sorry, I don't know about this. I don't know how it works. Don't tell them that. Give them the drugs. If it does work, then that's great.
And don't think too much as a patient. Just go and.
Yes, absolutely. I mean, I'm very suspicious of many claims, but I also absolutely trust my physician.
You have to, I suppose.
Yeah.
And of course, consciousness was something Francis Crick was working on, I think.
Yeah, well, as you said, I'm writing a biography of him. And I think one can blame him for a lot of this, the resurgence of interest in consciousness that has happened in the last 40 years since Stuart Sutherland wrote that rather acerbic little definition. So Crick, from his, he's mainly known for discovering the double helix, for his work on the genetic code and so on. But basically, when he was in his 30s, which was in the middle of the 1940s, so he's born in 1916, he started off doing a PhD on physics and viscosity in water and all the rest of it. And he wasn't interested in it. The war distracted him. He ended up building mines that would explode or not, depending if they encountered a magnetic field. So he was doing kind of very applied war work. And after the war, after a brief period in naval intelligence, he decided that there were two things that really fascinated him. One, the difference between life and non-life, so how you get the phenomena of life from chemistry. And secondly, consciousness, how we get thought from ultimately chemistry. And he wrote a really nice little kind of document in 1947 saying, these are the two things I want to do. Which one am I going to study? Well, maybe life, that looks a bit easier.
Okay.
And so he began that, and then through a huge chance, he ended up, he met Jim Watson, ended up very briefly working on the structure of DNA, and they were able to make their discovery. But eventually, after cracking the code all the work on the genetic code was done by the mid-60s, he then started to think about what am I going to do? And for various reasons, primarily to do with compulsory retirement in the UK, he worked for the Medical Research Council. And at the time it was 60. So he was going to have to retire at 76. And because he'd started working very late, his pension would have been really small. So he was very alarmed. One, he didn't want to stop work at 60. Secondly, he would not be able to live in the style to which he'd become accustomed. So he ended up going to the Salk Institute in La Jolla in Southern California near San Diego. And there he was eventually, from about 1980 onwards, able to work on neuroscience. And what he wanted to do was to come up with what he called the neural correlates of consciousness, that not to find the site of it or the seat or the network that produced it, but rather an activity that you could correlate with consciousness. And his initial work primarily was on visual perception. So seeing illusions was something he was very interested in, or immediate visual perception, because that must take place, within a few synapses of the retina. It can't take place in some really complicated calculation. So what is going on there? How can we measure this? And this was largely done in monkeys, or the experiments were done. He didn't do any of the experiments. And then in the last decade of his life, he became much more interested in more general theories of consciousness. And during this whole period, he was extremely influential for the whole of the neuroscience community. Encouraged the development of connectomes. He wrote an article in Nature saying it's outrageous. We don't know anything about the fine structure of the human brain. We know more about the macaque than we do about the human brain. We've got to fix this. So he encouraged that. And also a lot of work on neural nets, which are the kind of predecessors of today's chat GPT and the rest of it. These are very simple programs by today's standards, but many of the same people who developed the current, what are called large language models, like Geoffrey Hinton. So many people who now, like Hinton, argue that these chat GPT is conscious. It's not. It's just a parrot. Very, very clever parrot, but not that clever. They were involved with Crick back in the early 80s, and so he had his fingers in lots of pies. But partly because of his aura and prestige and his ability to express things very clearly, he ended up encouraging a lot of work, some of which I think has lost sight of the clarity that he had at the beginning of let's find neural correlates. And so we get these grandiose theories of everything, which are very hard to test or even understand. And yeah, anyway, so we've kind of skipped over quite a
Well,
bit.
yeah, well, you did tempt me when you said you were writing his biography. I can't wait to read that.
Well,
But
it'll be out next October.
okay, can't wait and see. Um, then the other one that we can understand a bit more because we know how nerves work is the electrical view
Yeah.
of the brain. And I was interested in this controversy that arose between Luigi Galvani and Alessandro Volta. I suppose that's where the genesis of this idea came.
Yeah. So what Galvani argued was that he noticed that if he was studying muscles in frog muscles, and if there was an electrical storm, the frog muscle would twitch, even if so there's a static electricity effectively. I mean, electricity had already been studied and people knew that it did stuff, but maybe it was just an irritant. If you get a frog muscle and you put acid on it, it will twitch, right? Because it's an irritant. It's not actually a neurotransmitter or anything like that. There's no acid in muscles, not in the neurons. So it wasn't quite clear what was going on, and Galvani and Volta disagreed over whether there was animal electricity, whether there was electricity in your nerves, if that was significant. And Volta decided at the beginning of the 19th century to do a bit of what we would now call biomimicry. He decided they knew that things like electric eels produced an electric shock. It's fairly obvious. There's a fish in the Mediterranean called the torpedo, which does the same thing. And you could dissect and you could see the organ that was responsible for it. It had this kind of layered structure. And so Volta decided to produce a model of that using bits of cardboard and bits of metal and bits of acid. And effectively, he created the battery as a way of trying to resolve this question, where electricity was coming from. And that then enabled the huge significance of this was that it then enabled people to produce controlled electricity. So if you think of what comes out of an AA battery, it gradually releases it discharges its electricity. Previously, the best way you had of storing electricity was something called a Leyden jar, which basically you got static electricity by rubbing amber with a cloth or something like that, and then the electricity would be in the jar, and if you touched it, then you get a big electric shock, like touching a cattle wire in the countryside. You suddenly get an electric shock. And whilst this was great for showing that, for example, if you get 400 monks, this is one experiment that was done, you get 400 monks holding hands, and if you get one of these Leyden jars at one end and you connect it to monk number one, then they jump in order as the electricity is going down this chain of whatever, 400, 800 meters worth of monk all holding hands. It's a genuine experiment that was done. But with development of Volta's batteries, then you can actually produce consistent current. And this led to both scientific experiments whereby you could get a hanged man. This is one of the things that was done in London. Didn't happen very often. So this was done by Galvani's nephew, Aldini. You'd get this poor man who killed his wife and child. He was hanged. And then he was immediately taken down from the gallows and taken into a room where about 10 members of the Royal Society saw Aldini get electrodes from one of these batteries and put it on either side of the man's head. And of course, his eyes opened and his arms would flail about and so on. So that really strongly suggested that electricity of some kind was doing something in our bodies. It was controlling. It wasn't just an irritant, because this was quite coordinated movement. And it also became a bit of a show, not with human bodies, I'm very glad to say, but with animal bodies. You could go to the London Theatre and go and watch somebody bring on a sheep's head or a cow's head. But the poor animal had just been decapitated backstage. They'd bring it on, and then an electrician, as he was called, would get the cables and connect them to the cow's head, and it's, you know, it open its mouth and grind its teeth and all the rest of it. And it's thought, there isn't decisive proof, but it's thought that in 1815, we know this was done at the Royal Institution in London, one of the big centres for public education in science, and a young woman called Mary Godwin, who was a teenager at the time, she was in the audience seeing one of these demonstrations with an animal skull. And some listeners may have already twigged, about a year later, she eloped with the notorious radical poet and womanizer Percy Bysshe Shelley. And on their honeymoon, it was very, very wet because there had been a huge volcanic explosion in the Southeast Asia, and this changed the weather around the planet. So they didn't have much of a honeymoon on the side of Lake Geneva in Switzerland. And so they sat in their chateau and they wrote ghost stories. And Shelley's was rubbish, and Shelley's mate's story was rubbish. But Mary Shelley's story, called Frankenstein, was fantastic. So there you go. We've got a bit of culture in there as well.
Interesting. And of course, the electrical, I mean, we can spend an hour, as I guess, on the electrical view of the brain, Edgar Adrian, Alan Hodgkin, Andrew Huxley.
Yeah.
But I would like to kind of go on to the concept of the brain as a perceiving organ. This had to do with the German Hermann von Helmholtz, who thought the brain plays a highly active part in constructing our perception or even quite straightforward things. And it goes on to almost show as if we don't have much of personal responsibility what we do. How much is that? How much is this concept of the brain not just perceiving but deciding what we see? How much of that is still accepted?
Oh, it's absolutely correct. I mean, the brain is not. So the problem is, you know, if you ask somebody how they perceive, how they see, then they'll probably come up with an idea. Well, you know, it goes into your brain and there's some kind of screen. And then you say, well, who's watching the screen? And they go, oh, okay. So, you know, we have this idea of a little mini me, and that, you know, this seems to be, our vision seems to be absolutely obvious. It's just coming in and then you see things. And then, of course, you do experiments, which is what von Helmholtz did. And he was the first person to identify the blind spot. So you've got all these neurons on your retina, but part of your retina, there is no sensation there, because that's where all the neurons gather together to form the optic nerve. And so if you do an experiment, you hold your vision steady and you move your finger back and forth, then there is a point around about there where you can't actually see it. But if you do that, if you just stare at a fixed point, there's not a black hole there. Yes. Your brain is a bit like kind of with Photoshop, it's kind of blurring it in, saying, okay, well, there's something there. And indeed, you know, you can see very accurately in the center of your vision, but out there, it's all kind of hazy. So clearly the brain's doing something. And what von Helmholtz realized is that it's coming up with a hypothesis about what must be there. And you can see this in something that I remember being absolutely intrigued by as a teenager. And it's still not properly understood. And this is an experiment we can do at home. Everybody's done. You shut your eyes, you press your eyeballs, and what do you see? You see light. And the reason you see, but there's no light there. The pressure, don't press too hard. The pressure on your eyeballs is activating the neurons in your retina, and the brain goes, oh, there's an activation in my eye. That's vision. That's all it is. It's just the activation of those neurons. So it's kind of like an illusion in that there is no light, but you see it, you perceive it, because that's what that is in your sensation. Another example of how the nervous system filters and changes what we perceive, I mean, it's something that I've worked on, which is sense of smell. There's one particular odor which is only detected by one class of neurons, our smell neurons in our nose, or high up in our nasal cavity. And some people smell this odor as very sweet, That's what I smell it like. Other people think it smells disgusting, like a back alley where men have been peeing. Other people can't smell it at all. And other people, again, thinks it actually smells quite sexy. And those differences in perception are all due to single base pair changes. So 2 letters of DNA are altered. Okay. And depending on how they're altered, that changes the protein on the receptor of these, which is on the outside of these neurons. So it's a bit like the lock. And the way that the odor turns in the lock to stimulate the neuron is slightly different. And that is all there is to produce these differences in perception. It's to do with slight chemical differences between us. And if you know somebody's DNA, you can predict how they will respond. And if you know how they respond, you can predict their DNA. And this led to me having what was probably the only really good scientific idea I've ever had, which was suddenly realizing that we could look for this gene in our distant cousins, the Neanderthals, because we've sequenced their genome. So these are people who went extinct about 35,000 years ago. And we can say something about their smell, their sense of smell. They would have hated it. That's the answer. They would have hated this odor. They would have think it smelled disgusting.
You know, there's a similar one with the dress which went on the internet.
Yeah.
But it was blue. I suspect it's a similar thing to this.
Yeah, absolutely. So you're making perceptions, and there are so many visual illusions. Our visual system is very well developed. It's very easy to control, much more easy than the sense of smell, which is why. Plus, there are experimental animals like cats that have been studied intently by neuroscientists, and have very, very clearly revealed this constructive aspect of the brain, trying to interpret it. Now, that must happen in hundreds of milliseconds, right? Because between stimulus and perception, and somebody clicking a button and saying, yeah, I saw that, or I saw X or Y, is about 200, 250 milliseconds. So the rapidity of the processing, and often the very immediate level of the processing, as I say, it's taking place either in immediate output of the retina or 1 or 2 synapses on. That is quite astonishing. But the brain is constructing the world around us. We're not simply absorbing it. Much of that is innate. We can't see ultraviolet light. We know it's there. We can't see radio, so we'd have to have huge, great big eyes to be able to see radio waves. So there's some things we can't see, and yet we know they're there. We can detect them using our instruments. So it seems like you're just looking out, but you're not at all.
I can imagine how far we can go down this path.
Yeah.
Okay, let's go to, I suspect that's the current concept of the brain as a computer. How accurate is it? Well,
it depends who you're talking to and what you mean. So if you're talking to a relative who doesn't have any kind of scientific training, then I think it's a good starting point, because it gives them some idea. But for any practical purposes, no, it's not a computer. I mean, just to start with, my computer is binary. My neurons are not. My neurons have got a very strong analog component. The more you stimulate a neuron, the more intensely it will fire. So it's not zeros and ones. Above all, my computer is performing calculations. We know this because we've made it do it. The brain is clearly doing something like that, and the computational model has been very strong. But I remember asking, okay, when Twitter was good, you could actually ask it sensible questions, and people would come back. If you were lucky, they'd either follow you or you knew them, and they'd come back with an answer to stuff you didn't know about. And so I remember asking, can anybody give me an actual example of a neural circuit, so almost certainly just composed of a handful of neurons, that is performing a calculation, computation that we know about, and we've been able to prove that it's doing something. And there are perhaps now 2 or 3 examples, and that's it, and mainly in animals, of how these circuits might work. So whilst we understand everything about a computer because we built it, the computational aspect of the human brain remains very mysterious. And there are different kinds of computations. There's trying to be able to distinguish a figure from the background. And then there's the computation, what's called Bayesian statistics. That is, you change your assumptions based on how frequently something has happened. If something's happened a lot in the past, then you can be pretty confident in general it's going to happen again. And so not every kind of calculation is equally valid. You don't need to recalculate things over and over again because you've learned them. You've got certain pathways that are now kind of strongly reinforced because of learning in the past. One clear example of this is something. If it happened to everybody's had something had this happen to. It happened to me when I was a child. I went out. We had cauliflower, which I quite liked, and then in the evening, for whatever reason, I vomited, and I could not even stand the smell of cauliflower for about 30 years because it just made me feel so ill. This is one trial learning, and it generally works with taste. And smell and being sick, and kind of the evolutionary advantage of this is very obvious. It didn't do me any good. It might not do it again. But that is so strong, and yet we have very little idea about in any system in animals. But it's very little understood, very little studied. But one trial learning, as it's called, you only need to do it once, and you're never going to do that again. Is amazingly powerful and shapes our behavior, and yet, although we've got a principal idea of how the nervous system is making that calculation, don't do that again. We've no actual idea about where it's located or how it's actually working.
Well, clearly, one of the main lessons of your book is we don't really know what happens. And I have to cite this quotation: despite a solid bedrock of understanding, we have no clear comprehension of how billions or millions or thousands or even tens of neurons work together to produce the brain's activity. What other lessons do you think you want your readers to take from the book?
Well, one, that this remains the greatest challenge that science and medicine face, understanding the brain. There's a bit about philosophy in the book. I'm not terribly interested in philosophy. Francis Crick said something rather pithy. He said, you should listen to the questions of the philosophers, but not to their answers.
The answers, okay.
And I think that's absolutely right, because their questions are always incredibly sharp. On the other hand, there are two things that the philosophers have been worrying about for millennia that we don't know the answer to. One, why is there stuff anyway? Why is the universe? Where did it come from? What is it made of? And as you probably know, the physicists are currently assume that about 80% of the universe we can't even detect. It's this stuff called dark matter. And the other question the philosophers worried about is, well, what is thought and how does it work? And we don't know that either. So one, it's incredibly exciting. I think the most interesting thing is to think about this aspect of metaphors and using technology to explain scientific developments, which we kind of have to do, but that's also limiting. So by thinking about when for example, the telephone exchange came along and the telegraph wire, people immediately started thinking about the brain and the nervous system as being like a telephone or a telegraph system. And that, once you think about it like that, now I know what's going down the neurons. It's a message, and that changes everything that you could think about. People couldn't think in that way about what was happening in neurons before the development of the telegraph system in the late 1830s, and then the telephone exchange. So each level of technology has helped us understand the brain in a different way. And that, when I talk to scientists about this, they're initially kind of dubious, and then they get it and they get really excited. And they always ask me, so what's the next big thing?
Yeah, what's the crystal ball show for this?
Yeah, because that means we're going to reinterpret stuff in the future. Our current knowledge will change when we get new technology. Well, the kind of glib and rather facetious answer to that is I've no idea. And if I did know, I'd be very rich and living on a desert island. I can't predict the future. But in fact, the final paragraph, which is very long, of the book, basically outlines all the possible routes there are towards greater knowledge. And basically, I put in everything. I don't know how we're going to get to future insights, but I was one, trying to be fair to everybody, because although I say I'm a neuroscientist, I don't actually work on the brain. It's too complicated. Even a maggot brain is complicated. I've just been studying these single neurons. So I don't have any skin in the game, right? Which has also enabled me to be quite kind of, I mean, even-handed with people. I'm not pushing anybody's particular theory. So I put in all the kind of techniques and approaches that there still are. And then I finished with a one-word sentence, which I stole, in fact, from the German philosopher Nietzsche. And Nietzsche is famously known for having very strange ideas, very powerful ideas, but also he clearly had various mental health problems and became very manic at times. And in one of his documents, he was describing to his fellow philosophers the future of philosophy and what they should do. And it was all this kind of pell-mell, crazy ideas. And then he just went, or... And so I thought, right, I'm stealing that. So the last word is stolen from Nietzsche, because I just thought that was what confidence to be able to finish by just saying, it's up to you. You've got to work it out. Maybe I don't know. And given that was kind of my overall theme of the book, I thought that was the best way of ending. But my view is that I still think that more reductionist approaches of very simple nervous systems, perhaps, not even a brain. So the example I use in the book is the lobster's stomach, which has 30 neurons, which produces 2 rhythms. Their activity produces 2 rhythms. And we know everything about those neurons, everything you could possibly want to know, how they're built, how they function, the genes that are turned on and off in them. We can take them apart. We can do all sorts of fancy stuff. We can model them, and we don't know how they do it. So that's the kind of challenge. Everybody says, well, this is how the brain works. Just remember the lobster's stomach. We don't know how that works. And that's the same in physics, right? Physics has something called the 3-body problem. If you've got 3 astral bodies, then their behavior becomes completely unpredictable depending upon the initial setup. Now, the problem is that we've been here in the past. I deal with this in the book. In the late 19th century, there was a great period of doubt from about 1880, 1890, and everybody was going, we're never going to figure this out. Maybe it's unknowable, right? Maybe we can never know how thought is produced. Now, I think that's wrong. But I can't prove it, right? It's just my confidence as a scientist that there's no sight, no hint of anything strange happening. In the end, it is just the activity of our neurons. So I think a bit of one kind of healthy disregard for more mystical explanations and confidence that how much we've understood through the scientific method, and this will in the end get us there, even though I personally have no idea how it's going to happen, and this is the work of centuries, perhaps millennia. I mean, it really is a long... Francis Crick thought we'd have cracked consciousness by the end of the 21st century. I'm afraid not, Francis. You're going to, he did bet, or some of his followers bet a lot of money that this would happen, on big case of champagne, 2 of the main people. And we still haven't. That bet's been lost by those who thought we'd figure it out. I don't think it's not for this century, I don't think.
Some humility and open-mindedness.
Yeah.
Future. Okay, before we round up, do you have any... I usually put a limit to 3 books that you kind of recommend for...
Yeah. So I've got a couple of books about the 17th century, because that's kind of, as I've hinted, that's when it all got really interesting. So there's this, they're both books of history, but I think they've got different things. So this is Robert L. Martinson's The Brain Takes Shape, an early history, which is, I found absolutely invaluable for trying to understand what people were doing in the 17th century. And then, as I've already hinted, one of the interesting things about, or one of the ways you can see how influential these ideas have been, because if it's just somebody had a great idea and they wrote it down in a notebook and then it's been discovered 200 years later, it wasn't important. You can see these ideas in culture, and this is absolutely fascinating. It's by is she a historian? She's assistant professor of English, Leanne Habeneck, The Subtle Knot, and this is the brain. So early modern English literature and the birth of neuroscience. So it's looking at the interaction between scientific knowledge and medical knowledge and dissections and so on in the 17th century and English literature in all sorts of ways. And then in a completely different mode. This is a fantastic collection of essays by the world's leading neuroscientists, The Future of the Brain. Okay. So it's got lots of short essays from people who work on neural nets like Gary Marcus, from people who work on neurotransmitters, all sorts of different approaches. Who have we got in here? Got the Mosers, who won the Nobel Prize. There's Gary Marcus, Kevin Mitchell, who's a geneticist and neuroscientist in Trinity College Dublin, who's written some fantastic books recently. Olaf Sporns, who's been working on development of ways of controlling artificial structures with the brain. There's Christoph Koch, who worked with Francis Crick. There's George Church, who's the interesting geneticist, and lots and lots of people. It's a really useful book published by Princeton Press. I think it came out in 2016, but nothing much has changed recently, so it'll still do. Neurobiology, 2015, neurobiology of language, understanding the cortex, recording from many neurons simultaneously from measurement to meaning. These are the kind of papers. Really interesting.
Interesting. Thank you very much.
You don't need to be an expert, right? It's for the informed layperson.
Okay, that's one for some late night reading, I presume, and maybe a review in the future.
Yeah, I think it'd be good.
Matthew Cobb, thank you very much for participating in this episode of the Neurology Lounge podcast. I'm very happy you accepted to attend, and I've enjoyed it thoroughly.
Okay, well, I hope the listeners enjoy it, and I wish you all the great success with your podcast.
Thank you very much. I was going to thank the listeners as well. I hope they found it enlightening. If there are areas of interest, they might want to check The Idea of the Brain is a very good book I recommend. And I will also pitch in my book, Surfing the Brain, a bit clinical, but interesting stories there. And for those who want to look at the academic side of neurology, you can check my website called Neuro Checklist. And to make sure you don't miss the next episode of the podcast, you might want to subscribe to the iTunes, Spotify, or YouTube channels. Until next time, I'm Matthew Cobb. Thank you very much for your time. I'm most grateful.
You're very welcome. Bye-bye, everybody.
Bye-bye. Thank you.